Hi class, welcome to Online EdVantage. I'm Dr. Scott Adamson, and please subscribe to our channel so you can learn more about line integrals. Yes, we're doing more line integrals today. If you've been following the series of line integral videos, you've seen that there's several strategies that we can apply depending on the context. I have another strategy here for you. So imagine this vector field, 2x plus 3yi, 3x minus 2yj, and we're going to travel, metaphorically speaking, through that vector field along a quarter circle in a counterclockwise direction from 1, 0 to 0, 1. And the question is, with the line integral is, metaphorically speaking again, as we travel along this quarter circle within this vector field, are we helped, hindered, or is it a neutral kind of a thing as we make our way along that quarter circle from 1, 0 to 0, 1. So before we even start computing, let's get a conceptual, visual sense of this using a graphical representation. So we find ourselves in the vector field 2x plus 3yi plus 3x minus 2yj. So you're looking at for any ordered pair x comma y, at that location we're going to output a particular vector, thus creating the vector field. And in this case, we are metaphorically again traveling along this quarter circle counterclockwise from 1, 0 to 0, 1. And the question is, as we accumulate the dot products along that curve, are we accumulating them such that the dot products would be positive, negative, neutral, 0? What do we think? So let's kind of go through it little by little. So we're starting down here at 1, 0. So as we travel along this quarter circle, notice that the vectors are more or less in line with the direction I'm going. The angle between the path along this quarter circle and the vector field is acute, thus creating a positive dot product. As we travel to here, I would still say we're more or less in line. There's an acute angle. But then as we get to, say, about here, the angle between the path along the curve and that vector at that location is about 90 degrees. So now the dot product would be 0. And then as we move from there into this region, now the angle is obtuse, and we're now more or less being opposed as we travel in this direction. And clearly right in here, we're traveling counterclockwise, and we are nearly directly opposing that vector. So for part of the time, we have positive dot products, 0 dot product, and then negative dot products. And it seems to me, my gut feel is that there's more negative dot products up here than there were positive dot products down here. So I have a sense that this line integral is going to come out to be negative. Let's go compute it and see. So the graphical demonstration suggests that this line integral should come out to be negative, but let's compute it and find out. So we're on this quarter circle, and the parameterization of a quarter circle would be cosine ti plus sine tj. And if you need to pause the video now and think about that, please do. Maybe go back and check out videos on parameterizing curves. But that is the parameterization of this counterclockwise circle of radius 1. And we're only going we're having a quarter circle, so t will just increase from 0 to pi over 2 to allow us to be restricted to that quarter circle. All right, a line integral starts with this. We need our parameterized curve, already have it. We need to find f at r of t. So we don't want to be everywhere in that vector field. We just want to be in the vector field on the quarter circle. So we'll compose the vector valued function with that vector field. So instead of 2x, it'll be 2 cosine t. Plus 3y, instead of 3y, 3 sine t I. So 2x plus 3y becomes 2 cosine t plus 3 sine t as I replace x with cosine t, y with sine t. Now, likewise, 3x, 3 cosine t, minus 2y, minus 2 sine t. So 3x minus 2yj becomes 3 cosine t minus 2 sine t as I compose the x and the y components in. Now remember, we simplify this and we'll just call it f, but really we know it's f at r of t to keep us in the vector field, but specifically on that quarter circle curve. Second piece we need dr. Now really it's dr dt. We're going to multiply the differential dt to the right side. We'll make sure we do that later. But dr, the derivative of cosine of t is negative sine of t. The derivative of sine of t is positive cosine of t. And so dr is going to be negative sine ti plus cosine tj dt. So now the line integral involves the dot product between those two. Now keep in mind, when we say f, we don't really mean f of xy, we mean f of r of t. It's just common to shortcut that notation and just say f. So we're going to dot f with dr, these two things. Now dot product, we're going to take the I component, multiply by the I component. We're going to take the j component, multiply by the j component, and produce this scalar quantity. Keep in mind the dot product is a scalar. So let's do that. When we multiply the I component times the I component, now we have to distribute that negative sine of t on through. So negative sine of t times 2 cosine t will be negative 2 cosine t times sine t. Negative sine of t times 3 sine of t, so minus 3 sine squared of t. And then the j component times the j component, again distributing that through. Cosine of t times 3 cosine of t will be 3 cosine squared of t. And then cosine of t times minus 2 sine of t minus 2 sine of t cosine of t. Now, remember, dr all got multiplied by that dt, so this whole thing has that differential dt attached to it as well. Now let's simplify this f dot dr. It's a little lengthy. Let's see, we've got a negative 2 cosine t sine t. We've got another minus 2 cosine t sine t. So what we really have here, if we combine those, let's see. Let me just write it in a nicer order too. We've got a 3 cosine squared of t minus 3 sine squared of t, and then minus 2 cosine t sine t minus 2 cosine t sine t. That would be minus 4 cosine t sine t. So there it is. Now finally, the line integral. We now need to sum up all of those dot products across that parameterized curve. Remember, it's the quarter circle, so t just runs from 0 to pi over 2. So we'll integrate 3 cosine squared of t minus 3 sine squared of t minus 4 cosine of t sine of t. Now, for the point of this video is not to work on our integration skills. The purpose of this video is to think about line integrals and what they do. Remember, we've already seen that the path along that quarter circle from 1, 0 to 0, 1 had some positive dot product, 0 dot product, but then it seemed like it had some more negative dot product, so it seems like this line integral should be negative. So let's just use technology to find that line integral. Grab Wolfram Alpha, grab Desmos, and just integrate this nice single variable integral, and you will indeed find out that this line integral is negative 2. So metaphorically speaking, to help you understand what a line integral does is this. If you are in a river and the vector field was the current in the river, and you were paddling along that parameterized curve, that quarter circle, you would feel like when you were done, when you got to 0, 1, you would feel like overall you had been fighting that current because of the negative line integral. All right, now we're going to continue working on this because this is actually setting us up for a special case about line integrals that you'll see in the next video.